All right, so we're talking about things that we've already seen for applications of double integrals. In the last video, we talked about volume under a surface and above a region in the xy plane. And then we talked about the volume between two surfaces. Finally, I wanted to remind you that you can actually compute area. And the area of a region R is a region of the xy plane. Its area is just double integral over R of 1 dA. And as we talked about in class before we all dismissed, right, integrating 1 is the one function where the area under that function is the same as the volume. So I won't do an example of that, but I wanted to list it in my applications. In this video, we're going to look at another fun application to density and mass. So let's go ahead. I'm going to jump down to this, and then I can move everything around later on. So if you have a lamina, lamina just means thin sheet. So this sheet is very thin, and it occupies a region D of the xy plane, and its density at each point is given by some function of two variables. So my density is given by p, actually I'll say rho of xy. I'm going to think of this as rho instead of p. I do want to assume that rho is continuous on D. So then the mass of this sheet is given by the following double integral, which I've written down for you. So that's kind of a fun formula to know and be aware of. In practice, coming up with this density function rho is obviously the hard part. Those are hard to come by. But from a theoretical approach, it's very useful to know that this is how you can compute mass. So I thought we'd start with an example of this. I meant to already write it down so I didn't have to write it on the video, but I forgot to, so let's just do it. We'll use this example for this and then the other thing we're going to look at today. So example, so let's find the mass of R if rho of xy equals x, and this lamina R is the region bounded by the unit circle in the first quadrant. So let's maybe draw a picture of our region first. All right, here we go. And it's just looking like this. Something, whoops, not a triangle. The iPad got me there. That's not very nice. Let's make a circle, and then I can erase the other parts that we don't want. All right, there we go. So this is my region R. I'm thinking of this as actually being this very, very thin sheet occupying this region. And its density is not constant. We're used to sort of thinking about materials having constant density, but especially for you engineering folks, right, that may not be the case. It may be that you are using some sort of material or construction where the density changes. Ours, the density depends on x. So the farther down the x-axis you go, the higher the density is. And so we want to know what's the mass of this entire sheet that looks like that if its density function rho of xy is just x. And so to find the mass, as we said before, the mass here is just you double integral over R of the density function rho of xy dA. So this one should be pretty clear to you at a glance looking at this that you're going to want to switch this thing to polar. And so I'm going to switch this as, well, R is going from 0 to 1, theta is going from 0 to pi halves. Rho of xy is just x. So I'm going to get an R cosine theta times an R dr d theta. And so let's see, I'm going to move this over here. This is going to be double integral 0 to 1, 0 to pi halves, R squared cosine theta dr d theta. None of these two integrals are that challenging. You can actually separate this completely. In fact, let's just see it. So the first integral, I can think about this as the integral from 0 to 1 of r squared dr. That's just going to be a third. And then the integral from 0 to pi halves of cosine theta is just going to give you 1. So this is just a third. The total mass here is a third. If you have any trouble following how I evaluated that, I highly encourage you pause the video, work out the computations. I'm trying not to do heavy computations in the videos just to save time. So I'm going to stop this video, and then we'll pick it up